So before we start with the proper theory, I want to do an example where we just try to measure the sizes of subsets of a certain set, the closed interval 0, 1. So this is a good first example of just an attempt and see what challenges there are. So can we define a function, let's call it lambda, that outputs numbers, which are the sizes of sets, and what you input is any subset of the interval 0, 1, which is reasonable. And that's a really vague term, but let's figure out what we want it to do as we go along. And we're definitely not going to achieve getting all subsets, but let's see which ones we can get. So to start with, so let me here put down some, I'm going to use this notation, a script A, and I'll explain why I'm using this style of script A soon. And here, script A is supposed to represent some subset of the power set of the interval. So we want this to be reasonable, and we also want script A to be large, to be as many sets as we can get in there. So we want it to be a large class of subsets of 0, 1. Okay, well, one thing you might start with is how about the sets like this? Like if you just have an interval. What should its length be? B minus A, right? So that it's pretty easy to make a decision about that. So if you have this, then define lambda of this to be B minus A. Similarly, for ones like this, intervals like this, or like this, or like this, we'll define lambda of them, so their length, to just be B minus A always. So far, that's 4 classes of sets that are now considered to be measurable, in the sense of we can apply lambda, our measure lambda, to them. So this is the first class of measurable sets, these closed intervals, where A and B are chosen so that this interval is inside the interval 0, 1. And let's call that one script A sub 1. And then let me copy this and define the other ones. Like that, so the same thing, but just the class of half-open intervals of different types, or these open intervals. And it seems like we can come up with an idea for what the size of a set should be when the set comes from any one of these, script A 1, 2, 3, and 4. So then currently our domain, our strongest possible domain for lambda here, which I'm going to call script A in the end, is the union of these 4, since we can handle these 4. But we can do better than that, actually. So if you have 2 sets, so hopefully this sounds reasonable. If you have 2 subsets of our interval 0, 1, and they are disjoint, then if they are measurable, if we have a definition for lambda of either of both of them, then we should be able to get a definition for lambda of their union. It should just be the sum. Right? Like, for example, we have a meaning, we have attached a meaning to lambda of 0, 1/3, right? And we have attached a meaning to lambda 2/3 to 1, right? This one is 1/3 and this one is 1/3. So since these sets are disjoint, it seems reasonable to decide that that's what should be the length of the union of 0, 1/3 and 2/3 1. That seems pretty reasonable. So if we apply this idea, then we can measure the lengths of more than just the sets showing up here, but also finite unions of disjoint collections of these sets. So let's define script A to be the collection of all finite unions. So things like this: union from I equals 1 to n of a sub I, where n, so it could be a union of length 1 or of length 2 or of length 27, any natural number n. And these things that are getting unioned are going to be coming from the, one of these types. So this is just the collection of finite unions of intervals, pretty much. So these are, you could call these elementary sets. This is what our textbook calls them. The elements of this is the class of elementary sets. So we define this. And there's nothing wrong with the sum that I'm writing down here. It's a finite sum. So we define this. I think there is a well-definedness issue to pay attention to here, which is, what if you can write something as what if you can take an elementary set, an element of this collection, and write it in multiple ways as a disjoint union of intervals? That can happen, right? For example, the interval 0 to a half or something could be written as just the interval 0 to a half, as a union of one thing, which is itself. Or I could write it as the union of two disjoint things like this. But we do get the same answer, and when we apply this definition. So here we would get a half if we applied our definition, since this is of the type here, and we said that we would just get the difference between the endpoints. And if we apply this one, if we view it this way, then we'd have to apply, if we view it this way and we apply this definition here, then we would say 1/4 plus 1/4, right? But we'd get the same answer. So that's not a proof, that's an example. That's not a proof of well-definedness, but I'm going to punt and not prove well-definedness rigorously, since this whole thing is just an example anyway. So yeah, you could worry about well-definedness here. So now we have defined lambda on all elementary sets. So there are a few interesting properties which we can notice that this lambda has. Let me go off to the side here. So notice that if I have two elementary sets, A and B, that are disjoint, then lambda of their union will actually be, so this is what I was mentioning earlier, that we should have this. We do actually have this for two elementary sets. What I was mentioning earlier was that we ought to have this, right? And I was saying, since we ought to have this, we have a way of extending lambda from being defined on just these collections of sets to being defined on the collection of unions of things coming from these. But after you extend it, then there's a question, which is, does this property, do we now still actually have this property for A and B coming from this larger class of sets? And we do. So to see that we do, write A and B as unions of, let's call them A sub I and B sub I from 1 to n sub B, I from from 1 to n sub A. So write them like this, where the A sub i's and the B sub i's are in there. So they're all these kinds of intervals. So the A sub i's and the B sub i's are all these types of things here. And we can do that because we're talking about A and B being in here, and this is the collection of finite unions of things from here. Then for A and B to be disjoint, we have to have that any one of these AIs has nothing in common with any one of the BIs. If there were something that were in one of the AIs and that thing were also in one of the BIs, then that thing would be in both A, which is the union of these, and in B, which is the union of these. Right, so all of the A's are disjoint from all of the B's. So then when we write A union B, if we write that as the union of all the AI's first, let me write it like this, so it looks like one big finite union, and then I write the union of all the BI's, B1 up through the last B, then this union written here is a disjoint union. And so since this is a disjoint union of intervals, by the definition of lambda, if I now apply lambda to both sides, by the definition of lambda, what I should get is the sum. The sum of these numbers. And of course, if you look at this portion of the sum, then that's lambda of A. That's how we define lambda of a finite union of intervals. Then if you look at this portion of the sum, then that's lambda of B. So that's the reason I say we still have this. And of course, what I'm showing here is pretty simple. I sort of skipped over the more notationally challenging thing to show, which is the actual well-definedness here. Okay, another thing to notice here is that is what happens with complements. So also notice that if, let's say A is a subset of B, and A and B are both in our class of elementary sets, so they're both finite unions of intervals, then, well, you can write B as A unioned with the part of B that is not in A, right? A union with B without A. Now, this is a disjoint union, right? These are disjoint. So if I apply lambda to both sides, then this becomes a sum here. So the length of B equals the length of A plus the length of the part of B that does not involve A. Okay, so subtracting this from the other side, the length of B with A deleted is the length of B minus the length of A. So that's a nice thing to notice that we have. And also, this shows you, I guess, that the length of A is less than or equal to the length of B. So the reason I say that is that the length of B is the length of A plus something non-negative. So lengths are always non-negative here, because we define the lengths of these super basic sets, the actual intervals, to be literally these differences, which are always non-negative. And we defined the lengths of elementary sets to be sums of those kinds of lengths. So sums of non-negative things, so always non-negative. So in our setup, no matter what, this will end up being non-negative. So lambda B is lambda A plus something non-negative. So lambda B is greater than or equal to lambda A. Okay, so these are some nice properties to keep in mind that we ended up having. If you did union two disjoint elementary sets, then the length of the union is the sum of the lengths. If an elementary set is contained in another elementary set, then, well, you have a reasonable inequality for lengths, and you also have sort of what you would expect for complements. So these all fall under what I meant at the beginning when I said reasonable. We want something reasonable, and these are nice, reasonable things. But one issue with the class of sets, which you could call measurable sets, so one issue with that class of sets that we've defined is that, although I don't know if you're actually allowed to call them measurable sets. We're going to officially define that in a moment. But one issue with the class of sets that we are allowing ourselves to measure is that it is not so large. It only consists of finite unions of intervals, and there are a lot more kinds of subsets of the interval 0, 1 other than simply finite unions of intervals. So how do we enlarge this set? Or to be clear, how do we enlarge this set that I'm pointing to here? So how do we enlarge the class of sets? How do we enlarge the collection of sets to which we can apply lambda?